Welcome to a review of descriptive statistics. So recently in statistics, we went over sampling and data, organizing data, and summary statistics, and recently started on linear models. So the organizing data and the sampling, we were looking at graphs, mostly frequency tables, relative frequency tables, and histograms based on each of those. Summary statistics, remember, statistic is a calculation you make based on a data set, a sample set. There's a whole bunch of different ones we have there. Places to go for review, well, under course information, there's the link to my notes page. And so this is part 1, sampling and data, part 2, descriptive statistics, and now part 3, linear regression. So you could take a peek at what I thought the highlights and some of my examples were there. You've got access to all your homework. You can redo anything you want by just selecting an assignment, and if it's already past due, then you can just go in and do more practice. The show answer button's always there, which is kind of nice. If you want to look back on stuff you've done before, go to the gradebook, click on your grade for that assessment, and it will show you what you last entered that was graded there. So hopefully you've checked out the exam 1 week 5 section. So I have some old exams I've given in the past, so you can see what kind of questions I might ask. The questions are going to be either similar to your homework, the application problems you've done, or the critical thinking. There's a practice exam that is pulled mostly from your homework problems, so that's just a summary of some of the homework you've done, and I threw a few extra problems in there just to make it a little more interesting. And then there's the take-home exam, which is now available to you. And here you're going to get a set of data to work with. They're all the same data, so I have it just listed as one big data set with gender and GPA, and then I made 2 more tables where I just take the females, so there's that 3.3 and the 3.8 and so on, and the males 2.9 and 3.5. So I just separated them out for you and made a note of how many females and males there are. So these are the GPA of some students at Puget Sound University. And here are some of the summary statistics I expect you to calculate. So you're going to calculate them and plug them in. You're going to search for outliers in a couple of different ways, and then compare the males to the females, and then read through this paragraph. Then you're going to write about what you saw in the data and include some graphics. If you wish, you could have a link to a Google Doc, or you could type everything up in here and upload images in here of your graphics. All graphics should be labeled well and commented on in your writing. If you have any questions, get in touch with me. So just an overview of the descriptive statistics that we've been working on. For this, I'm going to use a data set that I've linked at the end of the linear model section, and the data sets at the bottom. There's data for review. And when you get this data set, it will be view only, so you'll have to make a copy of it to play with it, or you'll have to download it and use it in Excel or whatever else you like to do. All right, so here's my copy here. I had started calculating some summary statistics based on the random sample. The original data, there's over 1,000 birth weights listed over here. It was collected from some hospitals in Philadelphia. So common summary statistics, I need to know the sample size. We need to know the mean, the standard deviation. And since you can't talk about the standard deviation without talking about the mean, we want the coefficient of variation, which is always the standard deviation divided by the mean. Other things I want are the 5-number summary, so I can make a box plot. Stack keys is a great place to go for a box plot. And then the range and the IQR to talk about, so for some measures to talk about variability. We'll also want to look for outliers. So the 2 procedures we have for looking for outliers are, so far, the 2 standard deviation rule. And that's just look 2 standard deviations below and 2 standard deviations above. So we're going to have a low, actually let's just call it minus 2s, and we're going to have a plus 2 standard deviations. Remember, you can't have standard deviations without the mean, and the computer didn't like the way I typed that. Let's try again. If you do a little apostrophe, then it will treat it as text, so plus 2s. All right, there we go. So to make those calculations, I'm just going to have to start at the mean and subtract 2 times the standard deviation. Let's blow this up a touch. And then again, starting at the mean, add 2 times the standard deviation. So those are the numbers I get. It's a little more decimal places than I need. So let's drop those down. 1 decimal place should be enough. Okay. So according to the 2 standard deviation rule, if we have any birth weights under 1900 grams, so let's say I would have to sort these to see that, but I can kind of tell by looking at the min, there's definitely at least one. So sorting these numbers, I have 100 of them in the random sample, and then I want to go to the data and sort the range with a hetero by birth weight. Okay, so let's see, below 1900, it looks like there are 3 of them that are underweight by this, so they're unusually low compared to the rest of the data. Unusually high, 2 standard deviation rule marks us at about 4465 grams. So if we scroll down to the end, 4465, it looks like I have 2 that are unusually heavy babies compared to the rest of the data. Other measure for unusual values or outliers was by using the IQR. So there we have what we call the low fence and the upper fence. And so the low fence, remember, was Q1 minus 1.5 times the IQR. And then I have the upper fence, which means go to Q3 and add 1.5 times the IQR. Right there. All right, so not exactly the same numbers as I have up here. So 1900 is below that, it's an outlier, unusually low. Here it's 1472, so the bar is set a little lower in the IQR. And every data set's different. These 2 methods don't necessarily agree. And then 4900 would be the mark for unusually high birth weights. So do we have any? That is above the max. So according to the IQR rule, there are no unusually heavy babies. All right, so we have 2 methods that say there are definitely unusually low birth weights. One method says there are unusually high ones. The other method says there aren't. And that happens. Let's look at a histogram. Not a line chart. Okay, so here's Google's first attempt at that. Let's zoom out to see it. So Google scaled by 500. Seems okay to me. And this part seems pretty nice and symmetric. Wow, it's almost perfect. But I do have a left tail, so this is skewed left. And then I might want to ask myself, well, why might this data be skewed left? Is there a possible reason? Well, I have heard of premature babies, and they tend to be lighter, so that could be the cause of these. And babies can't get too big because the mother has to contain them, right? There's a container that the baby grows in, and eventually the body pushes that baby out because it's big enough. Or I'm not sure exactly what the triggers are. We'd have to check with a biologist or a doctor. But it seems reasonable to me that a baby can't be too big, but a baby can be too small if it's born too early due to whatever complication. Other things we could calculate here are percentiles in addition to the quartiles. So maybe you've taken a kid to the doctor or you've gone yourself and you've heard, hey, your child's in the 90th percentile or 70th percentile. So let's check that out, percentiles for a sec. Percentile. So we might want to know what is the 90th percentile. So it'd be called P90. And so to calculate that, I start typing percent, and one of the options is percentile. Percentile wants my data, and then it wants to know which percentile. So that would be 0.9 is the 90th percentile. So a birth weight or mass of 3,864 grams would be the 90th percentile. So that means 90% of, based on the sample, 90% of newborns are lighter than 3,864 grams. Now, sometimes we go the other way. We're given a data value, and we want to find what percentile it's in. So here we have a percentile. We found the data. So we're going to go the other way. Often that's called percentile rank. And suppose that a friend tells me, hey, my kid was born at 3,600 grams. What percentile would they be, do you think? So based on this data, I could estimate that for them by using the percentile rank command. And so percentile rank, in this case, like before I grab the data, and then I say, okay, here's the number I want to compare to the data. And this tells me they would be in the 72nd percentile. The weight of 3,600 grams. Other things we might want to know is what percent of the data is within 2 standard deviations right here. So I could look at the data and try and find that by highlighting numbers that are bigger than 1936. So that would be starting here and going up to 4465. So I can just highlight them. 4465 is in between these two. And if I check out the count there, 95 of the numbers are in there. Well, 95 out of 100 would be 95% of the data is within 2 standard deviations of the mean. And we often check that to compare to normal standards. And usually it is about 95% of the data if the data is normally distributed. That's a whole nother question we'll talk about later, is within 2 standard deviations. So kind of fun stuff. Other things we could talk about, we could look at males versus females. So instead of sorting them by weight here, I could sort by gender and then see how different males and females are, or maybe they're the same. So highlight and data. Sort range, oops, I want to highlight all the data, all 3 columns. I don't really need the locator anymore. That was just to pick randomly some of those original data points. So let's see, data, sort range. It does have a header, and I want to sort by gender. So that'll put all the females first. All right. And then I'll color them just to help them stand out. We'll do traditional light blue for females and pink for males. I know that's not traditional. Shake things up a little. Okay. So I'm going to put these statistics right in the middle here. So I would like to find the mean and the standard deviation and the coefficient of variation, and perhaps let's look at the median too for now. So that would be average, and then highlight your females, and then do the same thing for the males, average, male, standard deviation. Remember, it's safe to use the STDEV one here. Females and males, STD, EV. And no, don't pick for me, Google. That's not what I want. I want these guys. And coefficient of variation means to take the standard deviation and divide by the mean. So we'll do a little comparison here. And then just the medians compared to the mean. Let's see, equals median females and males. Again, we could do a lot more, but I'm trying to make this video relatively short. All right, what do we got? Too many decimals for one. Make that easier to read. All right, so the average weight, again, these are the females here, and these are the males. Average weight of females is a little lighter than males. I don't know if that's true. Let's see, my sister was quite heavier than my brother or I when she was born, but this particular sample shows females lighter than males. Males have a higher standard deviation. However, you can only talk about standard deviation when you talk about the mean too. So then we need the coefficient of variation, and that should be a percentage. And 1 decimal point is enough. So what this says is there's a little more spread, average spread on the female than the male, even though the females have a bigger standard deviation. Males also have a bigger mean. Oh, I lied. It's the other way around. The males still have a bigger spread. Yeah, 20% is bigger than 18. Interesting. Okay. Yeah, so in this case, bigger standard deviation and a bigger mean still correlated to a bigger spread overall. What else? The mean was less than the median for females and for males. So that usually indicates when the mean is smaller, a skew left. Mean usually gets dragged toward the tail. So we did do a histogram for males and females. If we just do, let's see, just the females. Let's take a look at that. There's charts. And where's histogram? Yeah, that's got a bit of a skew left there. And let's try moving that out of the way. Put that right here, and let's do one for the males. Chart. Histogram. Yeah, definitely a skew left. Yeah, so the whole population has a skew left. The males have a skew left, the females have a skew left. So other things I want to look at is, you know, we can talk about comparing their spread, their means. So I just want you to make these calculations and then make some commentary about it. Is there anything else I want to mention about the commentary? Not at the moment. So take a look at your old homework, review that, review some of those practice tests, and have fun with statistics. That's it for now. Ta-ta.